Welcome back to Chang's Canvas. This is Chang. We will begin with angles and symmetry, move into length and congruence, use those ideas to understand right triangles, and finish with similarity, ratios, and the centroid. For every theorem, we will see what it says, use it once, reveal the proof hinge, and then let the whole figure move so we can watch the theorem survive. Theorem 1 is the triangle angle sum theorem. In every Euclidean triangle ABC, angle A plus angle B plus angle C equals 180 degrees. The shape can change, the total cannot. Suppose angles B and C are 48 degrees and 67 degrees. They total 115 degrees, so angle A is 180 minus 115 or 65 degrees. For the proof, construct a parallel through point A. Next, parallel lines transfer both base angles to the apex. Next, those three adjacent angles fill a straight line. Now move vertex A. All three angles change together, yet their sum remains 180 degrees. That invariant is the theorem. Theorem 2 turns the angle sum outward. In triangle ABC, extend side BC through point C to point D. Exterior angle ACD equals the two remote angles, angle A plus angle B. If the remote angles are 52 degrees and 63 degrees, their sum is 115 degrees. So exterior angle ACD is 115 degrees. For the proof, construct the parallel through point A. Next, parallel lines copy the remote angle B beside angle A. Next, that combined angle is exactly the exterior angle. Move vertex A and watch all three marked angles change. The exterior angle continues to equal the sum of the two remote interior angles. Theorem 3 is the isosceles base angle theorem. If side AB equals side AC, then the opposite angles, angle C and angle B, are equal. Always match a side with the angle across from it. If angle A is 44 degrees, angles B and C share the remaining 136 degrees equally. Each base angle is 68 degrees. For the proof, split the base at its midpoint and join A to point D. Next, the two half triangles match by side-side-side, or SSS. Next, their corresponding base angles must match. Move vertex A along the symmetry line. Sides AB and AC change together, while angles B and C remain equal. Theorem 4 is the converse isosceles theorem. If angles B and C are equal, then their opposite sides, AC and AB, are equal. This reverses the previous theorem and needs its own proof. If angles B and C are both 72 degrees, look across from point B to side AC, and across from point C to side AB. Therefore, side AC equals side AB. For the proof, bisect the vertex angle. Next, the two smaller triangles match by angle side, or AAS. Next, now read the corresponding opposite sides. Change the common base angle. The triangle changes shape, but the two opposite sides continue to match. Theorem 5 is the triangle inequality. In any triangle, the sum of any two side lengths exceeds the third. Equality is excluded because it would flatten the triangle into a line. If side AB is 7 and side AC is 10, then side BC, called X, must be larger than their difference, 3, and smaller than their sum, 17. For the proof, with B almost on segment AC, the third side approaches 10 minus 7, but a non-degenerate triangle keeps X strictly above 3. Next, as B rotates to the opposite ray, A lies almost on BC, and X approaches 7 plus 10, but stays strictly below 17. Rotate B while sides AB and AC remain fixed. The curve tracks X as it approaches 3 at one flat limit and 17 at the other, without reaching either value. For this example, every real value strictly between 3 and 17 works. 3 is less than X, and x is less than 17. Theorem 6 is side-angle-side congruence, abbreviated SAS. If two corresponding sides and the angle included between them match, then triangle ABC is congruent to triangle A', B', C'. The two marked side pairs match, and alpha is the included angle in both triangles. Side-angle-side, or SAS, makes the triangles congruent, so side BC equals its corresponding side B', C'. For the proof, match the included angle hinge. Next, align both fixed side lengths. Next, no freedom remains for the third vertex. Slide triangle A', B', C' onto triangle ABC. The two sides and their included angle cover exactly, so the third vertex has nowhere else to go. Theorem 7 is angle-side-angle congruence, abbreviated ASA. If two corresponding angles and the side included between them match, the triangles are congruent. The alpha angles match, the beta angles match, and the included sides AB and A', B' match. Angle-side angle, or ASA, makes the triangles congruent, so side AC equals side A', C'. For the proof, match the included sides and their corresponding endpoints. Next, draw the two rays fixed by the equal endpoint angles. Next, their unique intersection forces the same third vertex. Move triangle A', B', C' into place. Once the included side and both endpoint rays match, their intersection forces the same third vertex. Theorem 8 is side-side-side congruence, abbreviated SSS. If all three corresponding side lengths match, the two triangles are congruent, apart from a possible reflection. Both triangles have side lengths 5, 7, and 8. Side-side-side, or SSS, makes every corresponding angle equal. The angle opposite the side of length 8 is about 81.8 degrees in both. For the proof, start from the matched base. Next, use the other side lengths as circle radii. Next, the intersection leaves only a reflected copy. Slide one triangle over the other. All three differently colored sides cover their partners exactly, so the entire shape is fixed. Theorem 9 is the Pythagorean theorem. In a right triangle, the squares of the two legs add to the square of the hypotenuse, the side opposite the right angle. For legs 9 and 12, the sum of the squares is 81 plus 144, or 225. The positive square root gives hypotenuse 15. For the proof, drop the altitude from the right angle vertex to the hypotenuse. Next, each smaller right triangle shares an acute angle with the original, so both are similar to it. Next, use the two-leg projection identities, then add them and use AH plus HC equals AC. Watch the proof assemble. First the altitude, then two angle-angle similarities, and finally the two-leg projection identities. Adding them gives the Pythagorean equation. In every right triangle, a squared plus b squared equals c squared. Theorem 10 is the converse Pythagorean theorem. If the square of the longest side equals the sum of the other two side squares, then the angle opposite the longest side is a right angle. For sides 8, 15, and 17, 17 squared is 289. 8 squared plus 15 squared is also 289, so the triangle is right. For the proof, construct a right reference triangle at point C' using legs A and B. Next, by the Pythagorean theorem, its hypotenuse C' equals the given longest side C. Next, now all three corresponding sides match, so side-side-side, or SSS, transfers the right angle at point C' to point C. Compare the given triangle with an equal size dashed right reference. Its computed hypotenuse C' equals C. Side-side-side, or SSS, then transfers the right angle to the original triangle. Theorem 11 is angle-angle similarity, abbreviated AA. Two matching angle pairs fix a triangle's shape, but not its size, so triangle ABC is similar to triangle A', B', C'. Side BC is 8, and the corresponding side B', C' is 12, so the scale factor is 3/2. Side AC is 10, so side A', C' is 15. For the proof, copy side AB onto A', B', then draw a parallel to point B', C'. Next, the copied side and two given angles make the small triangles congruent. Next, the parallel copy is similar to the large triangle, completing angle-angle, or AA. Let the second triangle grow and shrink. Every length changes by one common scale factor, while the two matching angles, alpha and beta, stay fixed. Theorem 12 is the side-splitter theorem. If segment DE is parallel to side BC, then triangle ADE is similar to triangle ABC by angle-angle, or AA, and the corresponding side ratios are equal. Side AD over AB is 8 over 12, or 2/3. Therefore, side AE is 2/3 of side AC. 2/3 of 15 is 10. For the proof, parallel lines create two corresponding angle pairs. Next, those pairs prove angle-angle, or AA similarity. Next, similarity gives every matching scale ratio. Slide segment DE while keeping it parallel to point BC. The small triangle changes scale, but AD over AB, AE over AC, and DE over BC remain equal. A parallel cut creates a smaller, similar triangle and equal corresponding ratios. Theorem 13 is the triangle midsegment theorem. Join midpoint D on side AB to midpoint E on side AC. Segment DE is parallel to side BC and exactly half as long. If side BC has length 18, the parallel midsegment DE has half that length, so DE equals 9. For the proof, copy DE beyond E and join the new point F to point C. Next, the two triangles match by side angle side. Next, the parallelogram gives both the parallel direction and the doubled length. Move vertex A while D and E remain true midpoints. Segment DE keeps its parallel direction and its 1/2 scale. Theorem 14 is the angle-bisector theorem. If segment AD bisects angle A, then it divides side BC in the ratio of the adjacent sides. BD over DC equals AB over A. For the proof, draw the two perpendicular heights from point D to the sides AB and AC. Next, a point on an angle bisector is equally distant from both sides, so DP equals DQ. Next, using bases BD and DC, the triangles share the same altitude from point A, so their area ratio is BD over DC. Using bases AB and AC, the equal heights DP and DQ make the same area ratio AB over AC. Therefore, the two side ratios are equal. Theorem 15 is the centroid median theorem. The three medians of triangle ABC meet at one point G. On each median, the vertex to centroid part is twice the centroid to midpoint part. On median AM, segment AG is 2/3 of the full median, while GM is 1/3. Therefore, AG to point GM is 2:1. For the proof, define G, where medians A, M, and BE meet. Since M and E are midpoints, ME is parallel to point AB. Next, triangles GME and GAB are similar with scale 1 to 2, so AG equals twice GM. Next, now define H, where AM meets the third median CD. Since M and D are midpoints, MD is parallel to point AC, giving AH equals twice HM. Next, we have proved that G and H both lie on the same median AM and both divided 2:1 from point A. A segment has only one such division point, so H must equal G. Since G already lies on AM and BE, while H lies on CD, all three medians meet at point G. Move vertex A and recompute all three midpoints. The medians still meet at point G, and G remains 2/3 of the way from each vertex to the opposite midpoint. All three medians meet at the centroid, and each is divided in the ratio 2:1 from the vertex. That is the full set of 15. The real power is not memorizing 15 isolated sentences. It is seeing the connections. Parallel lines transfer angles, congruence creates rigidity, similarity controls scale, and midpoint constructions turn shape into ratio. Return to this board whenever you need the right triangle fact for a proof or a problem. Thanks for learning with me, and I will see you in the next theorem collection.